Linear Regression, Section 3. There are three parts to this section. One is to calculate the equation of the least squares regression line, which we've talked about a little bit, but now we'll talk through the process more officially. Determining whether a linear model is appropriate, and we'll use residual plots for that, and that'll be new. And then how we can use R squared to help us describe the data. So a graphic for this one would look like this. So we've talked about our calculators, or TIs, using linear regression to calculate it. We'll also use StatKey, and I'll talk about that in a moment. Residual plots are going to look like this, and you'll notice that the x-axis will look the same as your scatter plot, but your y-axis has this line right down the middle that has a value of 0. And you're going to talk about errors that are positive errors and negative errors, and how we interpret that data. And that data will help us decide if a linear model is appropriate. And then we're going to talk about R squared, and that's going to be the one place where we apply a sentence with regard to linear regression. So we said a TI can give you a regression line, but we will probably and most likely use StatKey most of the time. I've already showed you the link that would give us this. This is two quantitative variables. And if we simply toggle this right here, it'll give us the line that you see in red. Even if you don't toggle that, however, notice that in the right side you get the correlation coefficient, which is negative, which makes sense because it looks like a negative slope. And it's between -1 and 0. And if you look at the scattering of the data, that doesn't look like a really clear path. So that makes sense that it should be around a -0.5. So not very good correlation. But you also have the slope and the y-intercept. So you could write the equation with those two numbers right there, and that's how we can come up with our linear regression line. So how do we determine if a linear model is appropriate? Well, if you take your observed data, which is all of these right here, and you come up with a linear regression line, and you calculate the errors or residuals, which we talked about as being observed values minus predicted values, and we'll talk about that in a moment, you'll get a collection of residual errors. So like I said, your x-axis would be the same. So this would be miles. You'd have the same units from 0 to 160,000. And I want to go do another problem after this, hopefully clear. And the left side, the y-axis, is what's going to change. We would put this line down the middle, and that would be 0. And we would graph the errors. Now, we don't know what these go with because we have to have an x-axis or an x value that gives us the error. But these points would get put onto this graph. And they would be a positive error, a negative error, and so on. And then we would have a distribution like that, maybe. And I'll show you what that means more clearly in a moment. But let's talk about what pattern we're looking for, or lack thereof. If we have a residual plot created, to interpret it properly, here are three scenarios. And if you notice, two of these three have a pattern. So first of all, in B, we have this pattern that's all negatives below it. Down here, all negative residuals. Here's positive residuals. And here's where you have negative residuals for a while as you go along the x-axis. Then there's some positive residuals, the negative residuals. All these are patterns, which tell us that these are not good linear models. What we're looking for is something like this, where we see another scatter plot. The errors are a little above, a little below, no pattern present. So this is really what we want to see. So let's take a look at this example. Here's the relationship between the average number of points scored per game, X, and the number of wins for 12 college teams in the Southeastern Conference. Now the scatter plot is given right here. Okay, so we have this linear regression line drawn. We have the data plots. Looks like a pretty good linear fit. And they give us the equation right here. We'll talk about r squared in a moment, what that means. Now we are to calculate and interpret the residual for South Carolina, which scored 30.1 points with 11 wins. So they would be 30.1 right here or so, up to 11 wins. And I believe that'd be right about here. This is the point we want to look for. Now, what is the residual? The residual is the difference between this point here and the predicted, the line itself. So this distance from that point to the line is called the error, or the residual. Well, how do we calculate that? Well, we would take the equation, we would plug in the x value that we are wondering about, and in doing so, it kicks out 9.4. Now this value right here, 9.4, is the predicted value. In other words, that's the value you would have gotten right there on that line itself. Now that's different than the actual value, because they said it was 11. So if we took, and we said it order matters, observed minus predicted, so 11 is the observed value, they actually won 11, take away the 9.4, which is the predicted value of wins, and you get 1.6. Now 1.6 represents the residual, or the error. So if you notice this residual plot, we have our points per game. It's the same as this right down here. The axis is distributed the same with values, but again we have this residual. 0 error. If it's on this line, that means there's no error between observed and predicted. But if we went to 30.1, which again was right here, it gave us a 1.6 error, positive. So this represents a 1.6, and that's pretty close. And that's one data point. That's the error from one data point compared to the predicted and the observed. And we would do that over and over again. And if you look at that then, you'd say, well, what does the pattern look like? Is there a pattern or not? And it looks like that there is none. Some above, some below, like a scattering of things. So this would be considered a good linear, or a model that's a linear model, and it would be a good fit. So it's appropriate. Now in ending this, how do you interpret r squared? Well, r squared is your correlation coefficient squared. Now r doesn't give us much value in terms of units. It's hard to explain it in units to anybody who doesn't understand math, but r squared is actually pretty good. It represents a percent, 88%. Now this sentence structure is what you can use to interpret what that means. So we would say 88%, that would go here, of the variation in, and our y value was our wins. So 88% of the variation in wins is accounted for by the linear model relating wins to points per game. So our x would be down here and our y would be here. So 88% of the variation in wins is accounted for by the linear model relating wins to points per game. In other words, it describes 88% of the variation, and that's a lot of the variation accounted for. There's still some error there, but it's pretty good. And that would be a good sentence structure describing how related the data is. Henceforth, it's a good linear fit.